Claisen condensation. The base mediated condensation of an ester containing an alpha hydrogen atom with a molecule of the same ester to give a beta ketoester is known as the Claisen condensation. If the two reacting ester functional groups are tethered, then a Dieckmann condensation takes place. The reaction between two different esters under the same conditions is called cross Claisen condensation. Since the cross Claisen condensation can potentially give rise to at least four different condensation products, it is a general practice to choose one ester with no alpha protons. The ester with no alpha proton reacts exclusively as acceptor, and this way only a single product is formed. A full equivalent of the base is needed, and when an alkoxide is used as the base, it must be the same as the alcohol portion of the ester to prevent product mixtures resulting from ester interchange. There are two other variants of this process. An ester enolate reacts with a ketone or aldehyde to give an beta hydroxy ester, and B. A ketone or aldehyde enolate react with an ester to give a 1,3-diketone. Both of these are referred to as the Claisen reaction. A useful alternative to the Claisen condensation is the reaction of the ester enolate with an acid chloride to generate a beta ketoester. This is a coupling reaction. In the first reaction, two esters having alpha hydrogen condense with each other to form beta ketoester, which is an example of Claisen condensation. In the second reaction, uh, ester having alpha hydrogen reacts with ester having no alpha hydrogen to form beta ketoester, which is an example of cross Claisen condensation. In the third reaction, two tethered esters react to form cyclic beta ketoester, which is an example of Dieckmann condensation. Mechanism. In the first step, the base deprotonates the alpha proton of the ester to generate an ester enolate that will serve as the nucleophile in the reaction. Next, the enolate attacks the carbonyl group of the other ester to form a tetrahedral intermediate, which breaks down in the third step by ejecting a leaving group. Since it is adjacent to two carbonyls, the alpha proton in the product B ketoester is more acidic than in the precursor ester. Under the basic reaction conditions, this proton is removed to give rise to a resonance stabilized anion, which is much less reactive than the ester enolate generated in the first step. Therefore, the beta ketoester product does not react furthermore. This reaction shows the mechanism of Claisen condensation. Applications. In this application, lithium enolate of methyl homo Sacu- um, Sacudafniphyllite react with 2,8-dio dioxybicyclooctane acid chloride to form beta ketoester as an intermediate, which is subjected to Krebs decarboxylation to form sacu- sacudafniphyllene. In this application, an aldehyde and a phosphonate tetraester condensed to prepare the highly substituted naphthalene core, which reacted to form a diester which underwent a reaction to form justicidin B and retrojusticidin B in the presence of sodium ethoxide and THF ethanol. And in this application, gamma lactone condensed to form lithium enolate, which further condensed to form methyl 7 benzoyl benzoyl hydrate.